All right, last one. We have to find the free body diagram for a 3 Newton block of wood that's on a 14-degree ramp. So this is a ramp problem that has a force of friction of 0.3 newtons, and we have to determine on top of that the acceleration of the car as it travels down the ramp. All right, so um, for carts or for ramps, I always just draw it up and to the right. Doesn't really matter though. 14 degrees, and I always draw my object up near the top. So there is always the force due to gravity, and in this case that force of gravity is 3 newtons. And there is the force of friction pulling up. The block wants to slide down, so the force of friction is going to be pulling it up. And that's a force of friction of 0.3 newtons. And we'll have the normal force that we've got to figure out. So whenever you have the free body diagram or a force on a ramp, you have to break not those. We want to rotate our coordinate axis so that's our positive y and that's our positive x, perpendicular and parallel to the surface of the ramp. So Fn and Ff are perfect. We don't need to do anything with them. It's the force of gravity that we have to break apart into its pieces. And from the notes, the Fgy, which is this part, is Fg times cosine of the angle, and Fgx is Fg times the sine of the angle. So our Fgy, we want to solve for. Fgy is going to be 3 times cosine of 14 degrees, and Fgx will be 3 sine 14 degrees. So we got 3 cosine 14. 3 cosine 14 is 0.7273. I'm sorry, 2.91. Apologies. Reading the wrong one. 2.91, and the 3 sine 14, that's the 0.73 newtons. Alright, so we broke our Fg apart, and now we can create our free body diagram. So, as I told you, I keep the box as if it's on the ramp, and I fill in. My Fgy is one thing I care about, and that is 2.91 newtons, which means that since there's no other forces going up, my normal force is also 2.91 newtons. Going up the ramp, I have a force of friction, and that's my only force, of 0.3 newtons. And as expected, my downward force, the one that's pulling me down the ramp, is bigger than my force of friction, and that equals 0.73 newtons. Alright, so that's my free body diagram, right there. Oop, kind of. Didn't get it very good. Gotta work on my circles here. So, we have our free body diagram. Now we just have to determine the acceleration. So the acceleration is net force over mass. So I realize I have to figure out one thing first. I gotta figure out what the mass is. And I get the mass from the weight. Mass is weight over 9.8. So I take 3 over 9.8, and I get 0.31, really 0.306, but I'll round to 0.31 kilograms. Now I just have to determine what my net force is. Well, it's not coming off, up, or through the ramp, so my net force vertically is 0. Put that just down here. I know that my F net Y is equal to 0 because my total up force and my total down force cancel each other. So that has nothing to do with it. So my net force is only my horizontal force. And my net horizontal force is my total up force 0.3 newtons, minus my total downward force, 0.73 newtons. And when I say up and down, I mean up and down the ramp. All over my mass, 0.31 kilograms. So 0.3 minus 0.73 is negative 0.43 over 0.31. And I get an acceleration of negative 1.39 meters per second squared. And what does that negative mean? Well, it means that we're traveling down the ramp. That is our negative direction, so our acceleration should be stated as 1.39. You can leave it as the negative. Meters per second squared. I like to just abbreviate. DTR. Down the ramp. And there we go. That's our solution. Ramp problems are in some ways a little easier. Other ways a little more tricky. Depends on how you look at it. Break it apart, break the FG into its pieces, use that in a free body diagram to determine what our acceleration is. Hopefully this was clear, and good job.